The first step in the proof of the Giorgi's theorem consists in proving the following estimate, that if you have a solution U inside the ball of radius 1, then its L infinity norm is controlled in the ball of size 1/2 by a constant depending on dimension and lambda only, times the L2 norm of U in the ball of radius 1. So this is our goal. And we're going to prove this estimate in two simpler examples. The first one is really easy, is the case of harmonic functions. So assume U is harmonic in B1. Okay, and take a point X in the ball of radius 1/2. Then we can apply the mean value formula that says that U of X is equal to the average of U on the ball centered at X of radius 1/2 dy. Right? Now we can use either Jensen's inequality or the Cauchy-Schwarz inequality to conclude that this quantity itself is bounded above by the average of U squared over the same ball to the power 1/2. And this whole thing is obviously less than 1 over the measure of the ball of size 1/2 to the 1/2 times the L2 norm of U in the full ball B1, and we're done with the estimate in this case. Now let us turn to a more difficult example, which is going to be giving us the general strategy for the general theorem. So here we're going to assume that omega is a domain with smooth boundary, let's say a compact domain if you want, in Rn, and we're going to assume that the boundary of omega is a minimal surface. So it's going to be minimizing area. So we're going to assume this happens locally, so which minimizes area, let's say, in the ball of radius 1. So what this means is simply that, okay, let's assume that omega has this shape, and now we take a ball of radius 1, and if we take a compact perturbation of the boundary of omega, so let's say if we take this perturbation of the boundary, let me call this S, then the area of S is going to be less than, or greater than, sorry, the area of omega. Okay, so this is our definition. And now we're going to assume the following. We're going to assume that the volume of omega, which is contained in the ball of radius 1, is very small, smaller than some fixed constant depending on dimension only. Then, in fact, you don't have minimal surfaces. In other words, minimal surface. The intersection of omega and the ball of radius 1/2 is empty. So the picture is the following. You have a set omega, I don't know exactly how it looks like. We have the ball of radius 1/2, and then we have the ball of radius 1 right here. And we're saying if this area is so small, then this piece does not exist if the omega is a minimal surface. In order to prove this result, we're going to work with a dyadic decomposition inside the ball of radius 1. So we have the outer ball, which is the ball of size 1. Here's the ball of size 1/2. And then we're going to take a number of concentric balls that I'm drawing right here. Sorry if my drawing is not very nice. So here we have the ball of size 1/2. And let's call this radius here R index k plus 1. This one is RK, and this one is R, and we have again our domain omega, which is somewhere here. So what is RK? RK is just going to be 1/2 plus 1/2 to the k for k bigger than 1. And R is just some fixed radius that we choose between RK plus 1 and RK. And what we're going to do is to try to get a recurrence relation on the volume of omega contained inside the ball of radius rk. So how do we do this? Let's look at the volume of the ball of the domain contained in the smaller ball brk plus 1, and let me call that vk plus 1. So this is the volume of omega inside brk plus 1. And the first thing I can say is that I can use the isoperimetric inequality to say that this is bounded by a constant depending on dimension only times the area of the boundary of that same domain to the correct power n over n minus 1. All right? Now, if you look at the boundary of the sets, there are two pieces. There's this piece right here and this piece here. And by minimality, we can say that the full measure is bounded by 2 times the measure of the sphere intersected with omega, and this whole thing to the n over n minus 1. Okay, so this is the first estimate that we're going to do. Actually, we can say a little better. We can say that this quantity is going to be less than 2 times the volume of omega intersected with the ball of radius r to the n over n minus 1. And this is simply because vk plus 1 is bounded above by the volume of the omega intersected with br. All right, now let's look at vk. And vk, so this is the volume of omega intersected with the ball of radius rk. And so it's obviously going to be bigger than the volume of the annulus brk minus brk minus plus 1. Okay, now we can use slice integration, or the co-area formula, if you're aware of it, to say that this area can be computed, this volume can be computed by computing the area of each sphere dBr, where r varies from rk plus 1 to rk, intersected with our domain omega. So this is just a slice integration. And this whole quantity, by one of the mean value formulas, mean value theorems from first year calculus, is bounded below by the length of the interval rk minus rk plus 1 times the surface at some row between rk plus 1 and rk. Right, this quantity is 2 to the k plus 1 with a minus. And so in the end we get that 2 to the k vk is bigger than some constant, which is 2 here, times this area. But now you see this area is the area that we had in the first computation, so now we can say that vk plus 1 is going to be less than some larger constant depending on dimension only, times what? Times, let's say, 2 to the k vk to the power n over n minus 1. And here we have our recurrence relation between vk and vk plus 1. So at first, when you look at this, you tend to think that the 2 to the k is going to give you something very large as k increases. But be careful about this exponent here. The exponent n over n minus 1 is strictly bigger than 1. So what you can easily prove is that if v naught is less than some fixed constant, depending on delta only, then in fact v is going to converge, vk is going to converge to 0 at a super exponential rate. And I'll let you check this fact, which is elementary calculus.